Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 4.75. The problem statement says, the analysis of a coal indicates 75 weight% carbon, 17% hydrogen, 2% sulfur, and the balance, non-combustible ash. The coal is burned at a rate of 5,000 kilograms per hour, and the feed rate of air to the furnace is 50 kilomoles per minute. All of the ash and 6% of the carbon in the fuel leave the furnace as a molten slag. The remainder of the carbon leaves in the stack gas as carbon monoxide and carbon dioxide. The hydrogen in the coal is oxidized to water, and the sulfur emerges as sulfur dioxide. The selectivity of carbon dioxide to carbon monoxide production is 10:1. Part A, calculate the percent excess air fed to the reactor. Okay, so I've written down what I understand from the problem. We've got a stream here, got coal going in. This is the feed rate of the coal, W signifies a weight percent, while X signifies a mole percent. Okay. So we've got our weight percents that they gave to us, and then the balance was ash. All the ash goes out in the slag, and the sum of the carbon goes out in the slag. Then we've got a certain amount of air. The air that they gave to us was in a molar flow rate, and then these are the mole percents of, or the mole fractions of air, of oxygen and nitrogen. And then we've got a whole host of elements, compounds, and things coming out the stack, which is stream 4. Okay, so we've got carbon dioxide, carbon monoxide, water, sulfur dioxide, nitrogen, and a little bit of excess oxygen that doesn't get burned. Okay? All right, that's really important to note that not all of the oxygen is used up. All right, so we've got 4 different reactions here. We've got our hydrogen reaction, our sulfur reaction, and 2 carbon reactions. You want the same number of oxygens and sulfurs on both sides, or the same number of carbons on both sides. These ones are not too hard to balance, so I'll let you guys do that one. But let me know if you need extra help, then I can put a comment in or something like that. Okay, so part A, it tells us to calculate the excess air. Okay, so in order to calculate the excess air, we need to know how much oxygen is needed for complete combustion. Now, they didn't define in this problem if complete combustion also included the sulfur. So I wasn't 100% sure on what to do. I know sometimes you would include the sulfur, sometimes you wouldn't include the sulfur. I mean, you are combusting the sulfur, so I included it in my analysis. If your teacher or whoever says, no, we only count the carbon and the hydrogen, then my numbers are going to be a little bit off. There's not a lot of sulfur in there, so it doesn't change it that much, but if you are off by a little bit, that may be the difference. Okay, so how much oxygen do we need for complete combustion? Well, we need to know how much it takes to completely combust each of these elements. So we say, okay, how much carbon do we have going in? How much does it take to fully combust it? How much hydrogen do we have going in? How much oxygen does it take to completely combust that? Okay, and remember they gave us these amounts in weight percent, right? So we need to convert that into moles. Okay, that's why we have our molar masses here. Okay, so I've got our, oh man, this is driving me nuts. Sorry for that. Okay. So we've got our mass going in times the weight fraction, right? So that's kilograms of carbon. Then we divide that by the molar mass, and we turn it into moles, okay? Then we say if we have this many moles going in, what's our ratio of carbon to oxygen in combustion? It's for every 1 mole of carbon, we need 1 mole of oxygen to fully combust, okay? So 1-to-1 ratio there. And we need to change it. Remember, our mass flow rate is in hours, so we need to convert that into minutes because our molar flow rate of air is in kilomoles per minute. Remember up here, kilomoles per minute, kilograms per hour. Man. Kilograms per hour, okay. Okay, so that gives us the amount of oxygen we would need to fully combust all of the carbon, okay? So we start with carbon, now we do the exact same thing, but we do it with the hydrogen, okay? We say, this is our mass of hydrogen going in, now we convert that into moles. For every 4 moles of hydrogen, we need 1 mole of water. We need 1 mole of oxygen, okay? So every 4 moles of hydrogen, 1 mole of oxygen, convert hours into minutes. This is the amount of oxygen we need to fully burn the hydrogen. Okay, then we do the same thing with the sulfur, mass of sulfur, turn that into moles. We have a 1-to-1 ratio, look back here, 1-to-1, okay? And then we turn that into 60 minutes, right? That's how much oxygen we need to fully burn the sulfur. So it's not a lot, like I said, but it may change your answer slightly. Okay, so the total amount of oxygen we would need, we just add all these up, right? We just add those up, total oxygen, that's how much we would need to fully combust, how much oxygen we would need. It didn't ask for excess oxygen, it asked for excess air, right? So then we say, how much air would we need? Total air needed. Well, total air equals the total amount of oxygen divided by the mole fraction of oxygen, right? So then that equals, that's how much air we would need, 41.75 kilomoles per minute. Okay, so what's our excess air? We have to look at excess air is the difference between how much you feed and how much you need. Okay, and that is 8.24. So how much did we feed? We feed 50, I believe. Yeah, 50 kilomoles, right? And we need 41. Okay, so there you go. Oh man, sorry about that, guys. I'm not sure what's up with this program. Maybe I'll have to reset, like turn off and reset. But yeah, the program just keeps glitching out. So sorry about that. Hopefully you're still picking it up. Okay. Part B. Calculate the mole fractions of the gaseous pollutants, carbon monoxide and sulfur dioxide in the stack gas. Okay, this is the smallest wording that they have. It is the biggest part of this problem because you have to do all of the atomic balances and break everything out. So we're asking how much is in the stack, right? And that's going to be hard to calculate. Go back up here. They're asking what are these mass fractions or mole fractions, and it's based off of all this other information that they gave to us, so we have to do all of the atomic balances. So we're going to balance carbon, hydrogen, sulfur, oxygen, and the ash, okay, in order to calculate all of these things. So let's just start getting into it. So start off with our atomic balances. Okay, so we've got carbon. How much carbon do we have going in? Well, we need to know the mole, and we're doing these in moles, so we've got our molar flow rate, so somehow we have to convert our mass flow rate that they gave to us into a molar flow rate. But once we know what that is, then we can know how many moles of carbon are going in, and then we have a certain number of moles of carbon going out, the slag. Stream 3 is the slag? Yeah, okay. Stream 3 is the slag, and then we have a certain amount going out in the stack, in carbon monoxide and carbon dioxide. Okay. Then the same thing for the hydrogen, certain amount of moles going in the fuel, certain amount of moles going out, but all of this goes out as water, so that's nice, easy balance. Sulfur goes out as sulfur dioxide. It's a 1-to-1 ratio. Sulfur, 1 mole of sulfur has 1 mole of sulfur in it, and 1 mole of sulfur dioxide has 1 mole of sulfur in it. Okay. Then we do our nitrogen balance. Nitrogen goes in the airstream and it goes out the stack. Okay. Oxygen goes in the airstream, but for every 1 mole of oxygen, there are 2 moles of oxygen gas. There's 2 moles of oxygen atom in it. Okay. For every mole of carbon dioxide, there are 2 moles of oxygen. For every mole of carbon monoxide, there is 1 mole of oxygen. For every mole of sulfur dioxide, there's 2 moles. For every 1 mole of oxygen, there's 1 mole. For every mole of oxygen, there's 2 moles. Okay? That's where all these coefficients come from. Those are really important when you end up balancing this in the end. Okay? And that's all in the stack, right? Okay. So then we also look at our overall mass balance. Those were all just the atomic mass balances. Let's look at our overall mass balance, not our mole balance. We know how much mass is going in, and that's pretty much it. They didn't give us anything else, but we do have a couple of other things that could help us determine how much mass is going in the other ones. For instance, we know the molar flow rate of the air, right? So we could, and we have the molar components of air, right? So we can calculate what the molar mass of air is, and then we can calculate what M2 is based off of our molar flow rate. Okay, so that's what that is right there. For M3, they gave us this process specification, right? So we know based on how much mass is going in the mass flow rate that we can calculate what the mass of stream 3 is. Okay, that's great. So now we have the mass of stream 3 and we have the mass of the air going in. So if we know M1, M2, and M3, we can calculate what M4 is. Great, we are one step closer to getting our molar flow rate of the stack, because now we have our mass flow rate of the stack. That's great. Okay, now we're saying, okay, we said there were this many moles of nitrogen going in, that means there's this many moles of nitrogen going out. We already have our molar flow rate, so this is perfect. We have our molar flow rate of nitrogen. That one's the easiest one, right? Okay, so we kind of need to figure out what moles are going in, because in order to do all of our reactions, let's go back to our reaction equations. In order to do all of our reaction equations, we need to have stream 1 in moles, or else we can't do any of this math, right? So that's our next step. So we need to change stream 1 into a moles basis. We don't know the molar mass of ash, so we have to do it component by component. We don't know what the molar mass of ash is. They didn't tell us specifically what the ash was. Sometimes ash is a combination of a bunch of different salts that they don't burn, or other forms of like rocks and things like that. Just small amounts of it that ends up as the slag. Okay, so it's doesn't have a molar mass that we can pull out, being my point. Okay, so let's just find out what we can about starting with carbon. So we say, okay, we have this much mass of carbon going in. This is the molar mass of carbon, so N1 times the mole fraction of carbon, so this would be the number of moles of carbon in stream 1, is equal to this, right? And we do know all of these things, so we can calculate the moles of carbon in stream 1, which is this, okay? Then we basically do the same thing with the hydrogen, and we get the moles of hydrogen in stream 1, and then we do the same thing with sulfur, and we get the moles of sulfur in stream 1. Okay? And then in stream 3, that's the slag, how many moles of carbon are going out in the slag? So we know, okay, we have this many moles going in the fuel, this many moles of carbon do not get burned, and then we know later on, okay, if this is how many moles of carbon got burned, because this is how many didn't, and this is how many went in, right? So that's why that one's important. Okay, so now we have all of stream 1 in terms of the moles, like these important values right here that we calculated, and this is what we wrote all of our mole balances in, right? So now we use these equations, our atomic balance equations, and we start plugging in all the values that we do know. So this is our balance for hydrogen. We just solved for how many moles of hydrogen we have going in, okay? And this is our mole balance for hydrogen, so now we can calculate this unknown, right? So this unknown is equal to this. Okay, so then we do the same thing, but with our sulfur balance. Now we know how many moles of sulfur are going in, so now we know how many moles of sulfur dioxide are going out. This many, okay? Then we do the same thing for carbon, except for, remember, this is how much is going out the slag, so we just calculated what that was, so we know this, and now we have this, we don't know what those two are, so that's two unknowns in this equation, so we can't solve for anything yet. And then that kind of goes to this area. I just kind of broke that out, so now we have the two unknowns there. Okay, but they did give us a helpful bit of information. They told us that CO2 is produced 10 times more than carbon monoxide. Okay, so they gave us an extra equation. That is 2 equations, 2 unknowns. Okay, so we can solve for what those are now. 2 equations, 2 unknowns. Okay, so that gives us our carbon dioxide and our carbon monoxide. And the only thing we don't know now is how much oxygen, how many moles of oxygen are going out the stack. So now we use our oxygen balance here. Okay, and we know everything except for the amount of oxygen that's in the stack. So now we can solve for what that is. And we get this value. Okay. Finally, in order to know how many moles of material are in the stack gas, we just add up all of the moles. So we just solved for every single how many moles of each component are in the stack gas. So we just add all of those up, we'll get how many moles are in the stack gas. Okay, and that equals 53.7 kilomoles per minute. Okay, then we can, since we know this now, this value now, then we can figure out what the mole fractions are, right? So then you just take the value that we solved for and then divide it by the total number of moles. Okay, so now we have mole fraction of sulfur dioxide in the stack and mole fraction of carbon monoxide in the stack. Okay, and that's what they asked for in part B. What are the mole fractions? Okay, so that's the answer to part B. So let's move on to part C. Emitted sulfur dioxide by itself is a health hazard, but it is a more serious threat to environment as a precursor to acid rain. Under the catalytic action of sunlight, the sulfur dioxide is oxidized to sulfur trioxide, which in turn combines with water vapor to form sulfuric acid, which eventually returns to Earth as rainfall. Acid rain formed in this manner has caused extensive damage to forests, fields, and lakes in many parts of the world. For the furnace described above, calculate the rate of formation of sulfuric acid in kilograms per hour if all the emitted sulfur dioxide is converted in the indicated manner. Okay, so sulfur dioxide combines with oxygen and forms sulfur trioxide. Sulfur trioxide combines with water to form sulfuric acid. Okay, the molar mass of sulfuric acid is here. Okay, so we say this is our kilomoles of sulfur dioxide per hour. kilomoles of sulfur dioxide per hour. There's a 2:2 conversion, or stoichiometric ratio of sulfur dioxide to sulfur trioxide. So 2:2, those cancel out. Then we have a 1:1 conversion ratio of sulfur trioxide to sulfuric acid. And then we can convert moles of sulfuric acid into kilograms of sulfuric acid. And we get that there are 306 kilograms of sulfuric acid per hour dumped into the surrounding atmosphere from this plant. It probably sounds like I would not want 600 kilograms of sulfuric acid poured onto me, right? Because that would just be a puddle. But this is very diluted when it comes out of the plant, right? If you look at the mass fraction or the mole fraction, right? It's very dilute, even though it seems like a lot. If it's totally concentrated, it's obviously not totally concentrated, right? So it's not like super dangerous. The problems with this kind of just add up incrementally over time. So you don't really notice the effects at first until the forest starts to die, or the sculpture that you made is totally effaced because it's been, etched away. Things like that. So, or the building you're working in is just falling apart because the acid over time is just eating it away. Anyway, so those are some of the dangers that were caused by the sulfur dioxide problem that we've pretty much solved nowadays, just by limiting the amount of sulfur dioxide that plants are allowed to emit. Anyway, that is it for problem number 4.75. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.